When we do a lot of circuit analysis, we very quickly can generate many, many state variables. In fact, you can almost start to think about linear differential equations is a applied form of linear differential equations. And sometimes you get all sorts of different kinds of circuits, and then that leads all sorts of kinds of differential equations, such as the one below. You could generate a nice fourth order one with actually an arbitrary input. Why an arbitrary input? Because you're going to get all sorts of different kind of signals, and you have no idea what the signals will look like that you're going to process ahead of time. And you'd like to be able to find a formulation to figure out how to solve this. Now, this hasn't always been easy, and in fact, a century ago, this was a very tricky question. How do you handle these sorts of problems? And there are different ways of solving it and approaches. And what turned out to be very interesting, particularly related to circuits, was an individual by the name of Heaviside, last name of Heaviside, and he sort of looked at these concepts and said, I've got all these derivatives, these DDT kind of things. Why don't I just kind of call them a variable like S? And if I get it multiple times, I'll consider it a power. And then there's some interesting mathematics I can build with this to kind of solve for a whole range of inputs and even for arbitrary inputs. And eventually the whole conversation of arbitrary inputs requires, discussions like convolution, which is a little bit beyond where I'm going to take this conversation. But you can start doing all these ideas and you think, well, this is great. And you sit there and go, but the concept we're talking about is the Laplace transform. And you ask yourself, why wasn't it the Heaviside transform? Well, mathematicians didn't like Heaviside very much, apparently, and really thought everything he was doing was just kind of too creative and unrigorous, and just they couldn't do it. But what really infuriated them is that he was getting answers and solutions to problems that they couldn't get. Again, remember, if I find a solution to a differential equation and I can verify it, then it is in fact the solution to the differential equation. That's sort of this uniqueness concept that shows up. So this became a continuously increasing problem until somebody had found at least an allusion to the technique in something that Laplace had written. I believe it was an appendix, actually, of a discussion. And everyone went, oh, Laplace thought about it. Okay, we'll call it the Laplace transform and then we can use this. There is some very clear mathematics behind this and very good techniques. And the ideas are often to say, I'm going to move my entire problem into a transform space, and of course to be very careful, the transform thing is built around this particular integral where S is a complex number. Okay, and you could think about it carefully as that I'm looking at what orthogonal projections am I getting into into sort of this complex exponential space, because after all, exponentials are sort of the eigenfunctions of linear differential equations. And so we're going to kind of build it into that space in a general form. And then I'll often say, let me take the structure and transform it into that domain, do things in that domain, such as, oh look, my differential equations become algebraic equations, transform that problem to some extent, and then transform it back to the time domain. And so one can do this. And if you had to calculate this integral every single time, most people probably wouldn't choose this, although, who doesn't like doing an extra integral in the morning? But on the other hand, maybe it's nice to actually have these things where these are tabulated. And there's some sort of core properties that people use and kind of look at this. And so I have a whole number of properties described. There's a whole huge levels of tables you can do, but there's sort of properties that you often just start to remember because it just tends to make your problem solutions a lot easier. Now, the first key ones that kind of drove this is that the derivative of a function in the time domain becomes s times that function. And interestingly enough, the integral becomes 1 over s of that function. And you think, that's kind of cool. So I can get this algebraic structure. I can get various inputs, one of which is u of t, which is often called the Heaviside step function, which is basically just a step that goes between 0 and 1 that changes at t equals 0. This has just 1 over s as its function. There's some interesting properties to that. If I were to take e to the minus at, which of this structure, so a very classical sort of exponential decay where a is real, this transforms to just 1 over s plus a, and you're thinking, that's getting kind of interesting, because you often will, these are often solutions to linear differential equations, so maybe I'm going to get these kind of functional forms, and I transform back this way. I'll also get various functional forms that'll be quadratics, and those will go to sines and cosines, and really very key concepts. The other thing is that I can also do some interesting limit structures where if the function of, as it goes to time is an infinity, really looks like I take a particular limit in the Laplace domain as s goes to 0. In the other case, you get a case when s goes to infinity, gives me kind of what happens at t equals 0. These are very, very interesting properties, and you tend to use a lot of these different concepts. And it's kind of important to kind of understand these approaches, because we're going to use these kind of Laplace domain as kind of the basis to handle a lot of different frequency behaviors.